Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about why are we alone? Like that's a factual reality right now, so why? Let's understand some variables of it. So first we understand what are we looking for? We are looking for alien buddies. So we do not have alien buddies. Now here's the problem. There should be aliens, like for all data points. We are observing the whole universe. That's awesome, super awesome. But mathematically speaking, there should be aliens everywhere, or at least in few clusters, as in in one 1,000 light year there is one species there, 5,000 light year there is few species there. 3,000 light year plus they are spreading a lot. So 15-16 stars there has a civilization there. Oh, in that galaxy we have that. That should be the reality, but it's not. All our mathematics, even at the worst case scenario, as in you give the bare minimum value, and be mindful, many of these data sets are known because we are building observatories. So the fact how many stars are forming, we have good data on that. How many stars have planets around that, we have getting better and better data of it. The more observatories we launch, the more these numbers become refined. So that gets a scenario. It's like, where the heck is everybody? And then we come to another aspect of it. Quarters of scale number 2 and 3 would be impossible to hide. So even if it looks good in science fiction where it's like civilization is hiding first, impossible to hide anything in space. You can hide things in Earth, but you cannot hide things in space. Flat out you cannot. And not to mention, every amount of energy that is consumed eventually becomes waste heat. Meaning, even if you have GG amount of Dyson swarm and you are covering the whole star, you're absorbing 100% of the energy. Here's the deal, energy cannot be not destroyed. So over time, that energy will leak out as infrared waves. So we will see it. We'll see it. Like it will be giantly, weirdly glowing, infrared star that every detector we have will be like, bro, something is off. The energy output is infrared, but the amount of energy should not be possible in a, red dwarf, so to say. So it will not match, basically. The signature will not match. So we'll know we are looking at something like that, and then we can intensely look into it to observe it. So it would be flat out impossible, level 2 and level 3. So either everybody is stuck at level 1 or something is off. So we got nothing, flat out nothing. The best we have seen is this wow signal. And not to mention, there are so many hypotheses about that. And not to mention, the first rule of science is like you should be able to replicate it. We did not get a replication of that. So yeah, not good. And again, even if you get it, like these are way too sloppy. We need something absolute. We need something as absolute as like Moon, Mars, or something like that. Even if it's like a rare thing, it's like, but it should be like every observatory on the planet should be able to observe it, at least that much. Come on, like that's the bare minimum. It should not be like, oh, deorbiting orbit, debris that's like, it looks like a freaking flying thing. It's like, no. So as of now, we don't have aliens, but our mathematics say we should have aliens. So what's the problem? So physics level problem is displacement. What does that mean? That simply means universe is so goddamn huge. There is no number, there is no mathematics, there is nothing that can describe it, and no human can truly comprehend it. I can tell you one giant number with way too many zeros, but it does not. It's not comprehensible, so to say. So fundamentally, we just use one word, stupid. How huge is stupid? Do not try to comprehend it. How stupid? Well, it creates a scenario where speed becomes the limiting factor. Which speed? Light speed becomes a limiting factor, meaning we cannot go fast enough. And light speed is the limit of everything. Causality, basically, it inherently limits the causality. So many times you can find tricks to bypass the light speed. For example, you have one galaxy that is going x plus, another galaxy that is going x minus. Now this puppy is going at 0.7, this puppy is going at 0.7. Here's the deal, the gap in between, or the speed of the dark, is expanding faster than light speed. So you can cheat, so to say, in this way. But what is the causality limitation here? You cannot communicate. Like no matter what you do, action and reaction will not follow that. Meaning, let's say you take a laser and you shine it at the moon. I have found this amazing video. Please look in down below. You shine it at the moon and you spin it. Okay, you spin the laser. But here's the dot that is on the moon, that's traveling super fast. That's traveling faster than light. But here's the photons are still traveling at light speed. What does that mean? That simply means if you ever wanted to communicate, let's say you have 2 points on moon and they want to use this method of faster than light communication, they cannot. No matter what you do, anything that exceed light speed will not be communicatable. For example, two galaxies going apart, you cannot communicate faster than light in them. So there is always a law, like a freaking law, everything. So What does this translate to? This translates to you never have the ability to see in far. Basically, we take a telescope, we look. We do not look in far, we are looking in past. That's a very serious paradox that we have to deal with. Now, we humans are really good at understanding James Webb Telescope perspective. It's like, oh, it's looking so back. But apparently there is a mid spot where we kind of forget that every star that we are looking is also in light years. So we are not looking where Alpha Centauri is today, we are looking at where it was 4 years ago. And any star that is like 1,000 year or 10,000 year, same thing. So fundamentally, everything we are seeing that is far, we are also seeing in past. So flat out, this is a time dilation level of limitation on us. Dilation won't be the correct, displacement basically. We are temporarily displaced, meaning even if something right now is happening on Andromeda galaxy right now, as in like now, how the heck you define right now? Well, go make a time travel machine, go to the Big Bang, distribute clocks in each galaxy. So we are taking that clock. So from Big Bang, they are calculating to the Big Bang, we are calculating to the Big Bang. So now is now from the Big Bang. So now from that Big Bang, they may be having a level 2 or level 3 quarters of civilization and will not know it. And this is the closest major galaxy we have. Like if you are talking about some big daddy galaxy, this is a big daddy galaxy. You want to talk about something that is close by, this is closest by. Big galaxies when we are talking about. So fundamentally that is a paradox that you have to understand. Whenever we are talking about light year, it's a combined measurement. It's a measurement of two things at the same time, distance and time, basically how far back in time you are seeing. So if somebody says 4 light years, you are looking 4 years in past, and distance is 4 light years. That's why it's a combined unit. It's a very awesome way of, surprisingly awesome way to convey everything in one sentence. So if you're like, hey, Andromeda galaxy is like, how many zeros is that number? Let's talk. 2537000 years from us. That's how past we are seeing it. Meaning, if somehow you have a magical technology, let's say Q level technology in Star Trek, you go, bam, you jumped there, there will not be a galaxy there. Like, what the hell? What? That galaxy would have moved out. And it would have moved out. Like basically you have to calculate its trajectory in future that goes to like 2537, basically 2.5 million years in the future. There you have to snap. So you would be looking here and you will be like, okay, I have to go there. Then you may interact with this. So this is a very serious, realistic limitation. So even if right now the galaxy could be teeming with life, nobody, like everybody will also have the same limitation. Basically people in Andromeda galaxy will look exactly the same problem. Like, hey, Milky Way right now could have a dude talking in YouTube, but we cannot see that dude talking in the YouTube. It's like, that's the life. So this is a very critical displacement that we have to think about. Like we very good at like, oh, Big Bang. It's like, dude, every galaxy is also going through that. So fundamentally, right now we could have aliens in our next door galaxy. We'll have no idea about it. Like that's a very serious reality, and it will take 2.5 million years for us to get a confirmation. It's like, oh no, they have some, galaxy. So this displacement is a very serious, hard limitation. We cannot breach this puppy. Like this is the absolute. There is no going around it, and I'm talking about the nearest galaxy. Imagine going like 50,000, the furthest galaxy, or galaxies that, let's say, that's the other side of our observable universe. Yeah, no. That's a nope. That's a big ass nope. That's so far displaced. Yeah, no. So this is the first hurdle, the reason why we are alone. Like this cannot be breached. This is the permanent boundary that we cannot go past by. Then we come to, why don't we have FTL? Now let me be very clear. FTL looks amazing. No discussion, no hoo-ha about that. FTL equals amazing. And I really love this sequence of FTL drive. This is from a new TV show from Apple, The Foundation. And I just feel like it. And I watched on this TV, completely blacked out room, good sound, and I had speaker. I'm like, you would have orgasm if you had subwoofer there. So flat out, it was awesome. Like somebody is like, take money, give me a shot. So it's really awesome. Then we have the iconic Star Wars. Then we have iconic Star Trek. So all these things look good. There is no discussion about it. And they are very important tool for storytelling. No discussion about it. However, the laws of physics are like, yeah, bro, no, just no. Like you can create 10,000 loopholes. It's like, what if we do this Alcubierre warp drive or this and that? And it's like, no, it's just a big ass no. Like flat out no. Why? It breaks causality. Now, this is a bit complex to explain, but apparently if you travel faster than light, you are creating a paradox where you can actually contact your past and change the events. Be mindful, time law is built in such a way that you can only see the past. You can travel into the future, but nothing else other than that. So traveling faster than light allows you to breach that contract that we have with the Time Lords. So Time Lords are very, very serious puppy. They are like, no, no bro, you cannot travel faster than light. Now like, wait a minute, how the heck traveling faster than light breaches these sort of thing? I have linked a very amazing video down below. It's a bit complex, but you have to understand, same way that I have specified, you cannot communicate, you will be gaining the ability to communicate before the light reaches. So you broke causality. Thou shall not break causality. Now, depending how fast it is, let's just assume magically some species somewhere around the universe cracked it. They figured out a cheat code and they're like, bam, faster than light. If that is true, they would be able to take care of galaxy in few centuries, like whole galaxy, few centuries now. Like why it would be that fast? Even assuming they are only traveling at, let's say, 10x or 50x of light speed, or even whatever speed, even if it's just like, little bit faster, so time actually stops for them, they can colonize the whole universe without any hassle. Like it will be in few generations they can do that. Like, because again, let's look at a human example or this colony of our Milky Way. We have a good understanding that most things are like generally 50 light years to 100 light years. That zone is sweet spot. You will find a lot of stars. No matter where you see, that's the worst case scenario. Like in our case, we are very lucky. Like we 4.5 light year, boom. That's like first star, first hop we'll do. It's very close to us. So not every star would be that lucky, but generally every hop would be less than 50 or around 100 light years to get some good stuff. And if you have the technology, you will not have that stupid limitation of every science fiction writer where it's like, oh, they're not going to, stars. Every star, they are going to the planet. It's like, dude, you have the star, all you will see, does it have debris cloud? Does it have dust cloud? Does it have stuff around it? Yes, milk that puppy. And we can do that right now. So in future, how the heck people are, we are looking for habitable planets. It's like, no, go to any star, build the things you need. Maybe even build a planet, goddammit. So it's one of those things that allows, like, if you go to jump star and jump from those stars, it allows you to exponentially overtake basically over a galaxy. And not to mention faster than light speed because you are at FTL. So before the light of the core propagates far enough, we'll see it. Hey, something changed. Causality broke. We'll see it. But we haven't seen it. So there is a very good reason for it. It's like, it's one of those things that you can go, mind tricking yourself forever. But like reality, thou shall not cross the speed of light. Then we come to the horrifying filter, which we call the great filter. Because as our current understanding is growing with terms of microbiology, we are learning few things. We are way too goddamn good and we are way too goddamn close to abiogenesis, meaning taking unalive stuff, and making it life out of it. We are that damn close to it. We are like, if this is life, we are almost reaching it. We can see the trajectory that we took. Like we did this, we did this, we did this. It's like, damn. So this clarifies for us, fundamentally speaking, that abiogenesis, meaning unalive to alive, that jump should be super easy. Meaning there should be almost every planet that could do this should do this. Like abiogenesis should be super duper hyper easy. Every planet that could have like liquid water and all that jazz should have it. So it's one of those things. However, that being said, we are not interested in that. If we find a microbe in basically Mars, and let's say that microbe has different DNA structure compared to our DNA structure, that would be awesome scientific research. But that's not what we are truly looking for. Of course, it will change way too many things in biology, but it will not be like, whoa. That whoa is something like us, something that can jump between stars. That would be scary because we cannot actually do it right now. So we really want to be the first one. So there are many steps between a single alive stuff to us. So people have come up with basically I have linked the video down below of a professor who like apparently coined this term. So you should watch that, it's really good. So the idea is life. Like you take planets, not every planet will evolve life no matter what happens. Like some planets will have just bad luck, they will have bad relationship with their stars could be like, I don't want you, boom, star goes boom, planet goes kaboom. So something like that. Or they may be like, cheating around and then asteroid is like, bam, cosmic justice. So those sort of things. So planets does not guarantee you will get life. So that removes a lot of things. So that is first filter. Thankfully, we have crossed it. That we know we have crossed it. Then going from single cellular life, that is barely alive from our point of view, from that to multicellular, that's a big ass jump. Now, we have also cleared this. But that fundamentally means not every planet that cleared the life stage cleared this puppy also. You remove some puppy. Then you go from multicellular to civilization. Like us, we are here at civilization level. How many from multicellular to this puppy? We do not know. We do not have any data because all we know is one life form, that is human. So civilization, that's a very difficult puppy. And then we come to the colonizing universe part. Now this is a tricky part. Is this a great filter? Absolutely, because we have not seen anything that has crossed this. However, that being said, because we talked about displacement, there is a very good chance right now many species have already touched this puppy. We will not know about it. They could be far enough where it's like, dude, it's so far ahead in the future, it's pointless. So right now, this barrier is the barrier that says to us, is like, yeah, it's gonna be difficult. So we call these filters great filters. Now that creates a paradox, is like we do not know where we are. Basically, are we in a place where we have cleared the hard filters, or are we in a place we have to face our biggest challenge? Like the biggest challenge would be we go, let's say somehow we luck out and we actually jump to other star systems. We jump to, let's say, Alpha Centauri or other places, and we find civilization that looks too goddamn close to us. Some humanoids that look too goddamn close to us. That would simply means everything till this point was super easy except the colonizing universe part, meaning they boomed themselves or something else boomed them. So that's a very scary fact. But again, if we are seeing that evidence of that, that simply means we cleared it. So that's a, like, bittersweet kind of scenario. So we do not know where we are. We just do not know. The worst thing is behind us or ahead of us. That's mathematically unknown and unknowable until we are the one who jumps around. And there is a very good chance we went from here to there, that maybe we will find hundreds of planets. There is a very good chance we find hundreds and thousands and millions of planets that have life form, but none of them may jump from here to there. That would mean, like, between this multicellular and civilization level, there is a hard line of, like, intelligence growth. And again, intelligence is not a good metric for survival. So maybe evolution, natural selection does not work the same way everywhere, or we lucked out, they may not have lucked out. So you will have hundreds of planets with advanced life form, but none of them will send radio waves. So from our point of view, it's still a dead species, so to say. So that's a great filter. We do not know whether we have cleared this puppy or have to clear this puppy. Or maybe just because of the displacement factor, maybe there are hundreds of planets right now. They are ahead in their journey, we are behind in our journey. We will not know, neither will they. They will also not know unless they can breach faster than light travel, which I can guarantee you they cannot, because if they did, they would have taken over every single star on the goddamn universe. And very quickly, faster than light. So we come to the mathematical conclusion of all these data points, is that we are early, practically speaking. In terms of a practical data point, we are very early. So how do we know? How do you classify early or late in universe context? Well, we have a beginning point. Our clocks, basically the time as we know it, as a dimension that we live in, started at Big Bang. Okay, we get a point 1. That point 1 is like 13.5 billion years ago, or whatever the precise number comes to be in the future. Okay, we got the starting point. Then how do we know we are early? It's 13 billion goddamn years. And again, sun is also billions of years old. So it's not like, stars were not there. But you have to understand, we have to start elimination, the process of elimination. So how much lifespan stars have right now? Like as in our puppy, as in like sun, that is 8 light minutes away from us. How much life it has left? Not too much. So that's a bit worrying, around, 5 billion years. So yeah, we are sorted for a long while. So that gives us a reality, is that early universe were very hostile. How hostile? You start with the Big Bang, nothing, zills, zero. There is nothing there other than energy. At that point in time, you chill. You take a chill pill. Expansion happens, it chills down. At that chilling point, you start to create early stages of atoms. Then atoms chill down, they collapse, they coagulate, so to say, and then you have stars. Now that step itself is expected to be around 400 million years. So first, from 0 to 400 million years is poofed. You just poofed half a billion year almost, that you will not have any star. Now we come to the evolution of stars itself. Because again, what we had at that phase in time is just hydrogen, just raw hydrogen. That's not good enough. We need a periodic table. Hydrogen is just not good enough. So if any alien species comes and says we are 14 billion light years ago, 14 billion years old, that simply means they're coming from some other universe, not from our. Because again, they will reach a point where there was only light elements, as in only hydrogen. So how the heck you can have life in those sort of scenario? So what happened there? Stars happened. Boom happened. Now stars have this inverse relationship, meaning the bigger these puppies are, the quicker they go poof. So smaller they are, the longer they are. And the lifespan gap is described by this curve. And we use it like, solar mass to simplify the mathematics. So if it's very big puppy, like O class puppy, that is 10 to the power 7. Now if you have a tiny puppy, that is 10 to the power 10 zeros. So fundamentally it lives exponentially longer. So if you are like, let's say F star star, you're gonna live long. If you are G class, you're gonna live very long. If you are M class, your lifespan is so goddamn huge. O class will come and go. It would be like a basically insect lifespan compared to a human lifespan. That would be the range. So these stars are our checkpoints. This is how we understand how much time have passed. So you take blue stars, blue giants so to say, and they go boom. They are the first thing to be created because there is so much mass, so much hydrogen, so much stuff. Big puppy happens and big boom happen. Now this boom is very, very important for us. Why? Before this big booms, all we had hydrogen. Not good enough. We need way too many things than that. So where is the phosphor? Where is the sulfur? Where is stuff? Where is everything? So if you know the stellar biology, as in how stars go through its fusion chain, it does not just go from, basically hydrogen to helium. That's it. That's not how it starts. That's the level 1, but it goes to deep. It tries to fuse helium, then it fuses byproduct of that. Then it fuses carbon, oxygen, and it tries to go as low as iron. The moment it touches iron, that's the end sentence. Because you have to understand, there are two factors, basically two things that Thanos balances. Now these two things are gravity and the energy. Energy is like, thou shall not collapse. Gravity is like, thou shall collapse. So these two things are perfectly balanced. Now that perfect balance is unstable in time. Why? Gravity is passive force, meaning it will be there. There is no off button on that. But energy has an off button, meaning you run out of fuel, poof. So what happens is you take hydrogen, you boom that puppy, you get helium and you get a lot of energy. Now here's the deal. Eventually you're gonna run out of hydrogen. Okay, you ran out of hydrogen. What happens there? Then star loses because reactor turned off, star loses. The gravity is like, I get you, bitch. It starts to compress that puppy. And helium is like, whoa, 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 matter, still here, bro. Come on. Boom. Second boom. Now that hydrogen starts to go even deeper and even heavier, heavier, heavier. This works perfectly fine until we touch the last element, that is iron. The moment iron happens, still same thing happens. Iron gets fused into heavier stuff. Unfortunately, it does not give energy. It consumes energy, meaning you're running out of energy exponentially quicker. Ironically, you maybe have a scenario which I do not know how many people have clarified it, but like apparently that's how star's core reaches a point where it becomes cool, relatively speaking, because again it's absorbing energy, and boom, the collapse happens. That collapse creates what we call nova. Now it could be supernova, it could be hypernova or basic bitch nova, so that's up to you, but it does create that. And this nova event is so powerful, so high energy, this creates everything that we see in the periodic table, be it your uranium or be it tungsten and all that jazz. Everything that is heavy, heavier than basically iron. Again, people who do stellar physics, they can explain precisely. I cannot be precise enough. So that's how we get the basically elements. Then that dust that they created, basically this dust cloud goes there, settles. New stars are formed, new dust cloud is formed. In that dust cloud, new planets are formed. That's how Earth came to be. So we have to wait at least 1 or 2 generations of basically O class or B class to come to life, go boom, create enough heavy material, come to life, go boom, create another batch of heavy materials, basically fertilize the universe with basically the periodic table. Only then we can expect a future where we have complex stuff. I'm not even talking about life, I'm talking about stuff. Just the complex stuff requires a star to go through its whole lifespan, go boom at the other end, and hope not enough of them go boom in such a way where they're creating way too many basically black holes, because again black hole could consume some portion of it, because again this boom can create a black hole at the center, but it will only consume small part of it. The ejection velocity is so high that it will be there. So that's how we forge basically the heavier parts of the periodic table, be it lead, platinum and all that stuff. So that's how we get that. Now, early years is flat out not viable. Now, how many years we have to remove from Big Bang? We know few billions is just guaranteed gone, like 5 billions gone. So that gives us like barely 10 billion. So we know for a fact at very early, nothing can happen. Early stages of stellar evolution, we have no data point, because again, you have only one element, so nothing is there. Then you have to wait for a star to go its complete life cycle, then populate the whole, current generation galaxies with enough heavy materials to do heavy stuff. That will require like a whole generation. So you are easily removing billions and billions and billions. So it creates a viable reality where we may be the ASAP variant, meaning as soon as possible. We were possible now, we came to be. Of course, filters are still applicable because there could be a star that is, let's say, K class. It has so long lifespan. It has multiple planets. Everything is awesome. But it has a one side effect. It's like, asteroids keep making love to it. It does not have the bodyguards or vacuum cleaners that we have. We call them Jupiter and Saturn. Those are good vacuum cleaners. Top quality, 10 on 10. So those puppy clean us our, our ecosystem, so to say. So we do not have random giant ass asteroid making love to us all the time. So we do get love from them once in a while, but generally Jupiter and Saturn, they're good. They're good, strong bodyguards. You may have a scenario where it's like that's not the case, and be like, boom, you have life, everything is happening. Imagine this way, like we are in the Roman era, and an asteroid is just like surprise, boom. So that's a serious reality that we could be ASAP variant, meaning it could happen and it did happen, and there is a very real possibility. If we are ASAP, others are also there. But only difference is we are so displaced in space and time that we cannot see them. That's why all of us, basically all variants of a life form that is advanced enough as our current state, will be asking the same question. Where is everyone? Especially if they are Andromeda galaxy. Maybe there is a version, dude, there's like an Andromeda galaxy they are watching on YouTube. So we'll see. So this was my presentation, why we do not have any aliens. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.